Recently, I encountered a question. Is it possible to write classes without knowing the member variables ahead of time? It turns out there is, and it's actually kind of surprising. It's hiding in plain sight. But first, some context. So what is the context to this? So I am writing a deep reinforcement learning framework where, of course, we have to have a replay memory. Now, the way I like to handle replay memory is to use NumPy arrays. The reason for this is that NumPy will pre-allocate memory when you define the size of the array. It's going to make sure you have enough RAM to actually accommodate the stuff you want to store. This is very useful if you're restoring screen images in, say, the Atari library. If you don't have enough RAM to store 1,000,000 transitions, you don't want to try to store 1,000,000 transitions because it's going to crash your system and you're going to stop training and it's going to be a big mess. So NumPy arrays takes care of that for you. It makes life a little bit easier in that respect. But the downside is that we're going to have to define all of these arrays when we instantiate the class itself, when we define the class itself. And so we have to anticipate beforehand what the end user, in this case us, is going to want to store. If you want to add something else, then you would have to add in an additional field. But then if you go back to an old algorithm where you don't need that, then you just have an extra member variable hanging around and it's not very clean code. For a specific example of this, we have PPO memory. So in PPO, we also want to keep track of this variable probs, which is the log of the probabilities of the actions taken, and that's for use in the update rule of the PPO algorithm. So we have an extra member variable we want to keep track of, and notice we're also not using NumPy arrays here because we have a finite horizon over which we're saving things, and so memory constraints aren't really a concern. But we do have an extra variable, and so we have two classes of memory, and that's kind of ugly, right? Suppose you want to have a new algorithm where you keep track of some other parameter like intrinsic rewards, for instance, due to curiosity. Are you going to define another class still that has an extra member variable? Not very clean, not very elegant. Now there is a solution to this, and we're going to cover that in this video. To get started on that, let's first of all, we have to deal with one other problem, which is versioning. So in recent days, a lot of my code has started to get brittle with respect to underlying dependencies because NumPy changes stuff, Gym changes stuff, PyTorch changes things, and my old code is no longer forward compatible, and so it's a bit of an issue. For the purposes of our tutorial here, what I want to do is take a look at those three packages and see what versions I'm using so that we can all be on the same page. So we want to know NumPy, we want to know Torch, and we want to know Gym. And so you can see I'm using Gym version 0.18.3, and this is a deliberate choice. The reason is that I believe after this version, Gym lost the rights to or no longer has the rights for whatever reason to the Atari content, and so the Atari ROMs aren't included by default with later versions of Gym. And you can deal with that by downloading the ROMs separately, importing them. It's not hard, but it is a process, and so I'm opting for the easy route using 0.18.3, so that is important there. NumPy version 1.21.5. That's not such a huge deal. They haven't made significant changes, I think, up and through version 23. So not a huge deal, 1.23 that is. PyTorch 1.7. I have been experimenting with newer versions of PyTorch and stuff does break. So please be sure to be using PyTorch 1.7.0 or an earlier version. I would recommend creating a virtual environment and installing these packages so that you don't break anything on your main install if your particular code relies on newer versions of these packages. Other thing I want to do is I want us to go to my gist or gist linked in the description below where I have this code available for you, which is basically enough code to do a fully functional deep Q-learning agent. I don't want to rewrite the entire agent on this video because it's not pertinent to what we're doing. What we want to focus on is the actual memory for our agent. So all that out of the way, make sure you do that git clone of that gist, and then cd into that directory, rename it if you have to because it has a rather long, ugly name, just the way Gist handles it. And then we're going to take a look at a new file. We're just going to call it type. We're going to have a couple of classes, something very simple, nothing out of the ordinary. Self.fields equals a list A. And then let's have a class B that derives from A. Call your super constructor and then say self.newFields equals B. and then x equals b, print x dot fields, print x dot new fields. If you run it, you get precisely the output you would expect, A and B. Okay, so it turns out that what if we don't know that we want to save new fields later on? Suppose that we have our base class A where we have some basic parameters that we know we're going to need, but then B is the class where we want to actually have the dynamic members added. So in other words, if you look here at this class, things like the mem size and mem counter, you know you're going to need. You know you're going to need a function to store a transition, and you know you're going to need a function to sample the buffer in some form or fashion, right? So you know you're going to need those things, and then you can have a derived class where you have the user define everything else that they want to include. How would you do that? So the way to do that is actually pretty interesting. So it's upset because I don't have 2 new lines, and then I haphazardly slap at the keyboard. The way that you do that actually is hidden within plain sight. So there is the type keyword. So if we say x equals b, and if we print the type of x, then we can see that we get class main.b. It turns out there's another way of using the type keyword, and that's why I've called this file type. So let's start over here and get rid of all of this, and then think about how we can use type to define a class. So we can say A equals type. The name within the global scope is going to be A. We want to pass in an empty tuple, and then we can pass in a dictionary where the key is fields and the value is A. And of course I have a missing bracket there. And then if we say x equals A, print x dot fields, what will we get? Well, of course we're going to get the list A. Now we may be onto something. So if you take a look at this, you see that we can define a class on the fly within a program, right? We can have, say, a dictionary comprehension in here where we have the user pass in some parameters to a function. Say they have a run file where they define what they want to have for fields and values, and they can pass that into the type keyword to actually generate the class. Then we have one other question. How do we handle the stuff we know we're going to need, like the sampling, the mem counter, stuff like that? That comes into play with this empty tuple here. So this empty tuple is where we pass in the inheritance dependencies. So if we do something like, good grief, b equals another type. Oh, good grief, my hands are all out of whack. Type b, and that derives from class A. You have to save it as a tuple. Then you say new fields, and that's a list of elements B. Then you can say x equals b, print x dot fields, x dot new fields. And then of course we get our A and B. Pretty interesting stuff. So this seems to hold the key to what we want to do. So the idea is going to be that we're going to use a regular class definition, a generic buffer class, to handle the definition of our basic interface, where we're going to have a basic constructor that takes into account the memory size, the memory counter, and the actual fields that we want. And then we're going to have the type keyword that comes into play later that allows us to define what we want to save on the fly. So the other thing we have to worry about before we do that, I don't want to forget so that it's not unclear to you, is what if you don't know the actual parameter ahead of time? So if you don't know that the user is going to save probs, but they have a list where they define that, how would you know? You can say something else. You can actually say print get attribute b and fields. and you get that fields variable. So the get attribute function will be another function we want to make use of in this particular project. So now we have all the parts that we need. So let's take a look, do a list. You can see that I have a generic.py file, and in here I have everything we're going to need for this particular project. So the first thing we have to do is our imports. Obviously we're going to need numpy, and of course we want to actually define something for our class. So we need our initializer. That'll take a max size, a batch size, and the fields that we're actually going to instantiate. So we're going to say self.memSize good grief equals max size, mem counter equals 0, batch size equals batch size, fields equals fields. And then we need a function to store a transition. And again, we run into a problem. So we don't know how many things the end user is going to want to save. So in this case, I'm writing my own framework. I don't know a year from now if I'm going to need to save 2 additional parameters above and beyond the state action reward, new state, and terminal flag. So how can I define a set of parameters for this function? So it turns out what I can do is just say items, where I've assumed items to be of type list. So we're going to pass in a list, and we're going to say index equals self.memCounter modulus mem size for item, field, and zip items and fields. Now our get attribute comes into play. We want to get the attribute of the particular field for that index, and we're going to set it equal to item and increment our memory counter by 1. Let's dissect this code a little bit. So the items are a list, and the fields are the string representations of the things we want to save. So fields are new fields in our example with the basic trivial type.py file. And so we assume that items and fields match up 1-to-1. For every field, you have to have a corresponding item. Otherwise, the zip is going to go wonky, and it's not going to give you the results that you want. So we're going to say get the particular field of this object at the index element and set it equal to item. And again, we are assuming that it is an array or a list at the very least. And then increment your memory counter by 1. Now, this is equivalent to this code right here, where we have all of this stuff, where you have the index, that's common, but then all these other lines get taken into account with this for loop here, where we're zipping over items and fields. And of course, the next function we want is a way to sample our buffer. Now, the first thing we have to know is what is the index of our last filled memory. So we want to say max memory equals a minimum of either the mem counter or the mem size. And then say the batch is mp random choice up to max mem integers. We want to get batch size number of them and replace equals false. So if we draw a number, we don't want to draw it again. We don't want to duplicate memories. Then we say our array of memories is an empty list. So for each field in self.fields, we want to say array.append get attribute self field sub batch, and then return that array. Wow. Okay, so this is the equivalent of our sample function. So down here, where we have this iterate over, I have to enumerate each specific type of array, take the batch elements of that, and then return a list or a tuple of states, action rewards, new states, and terminals. This is equivalent to that. You can see the matching code is here. Those two lines match, and then all the other stuff is taken care of in this single for loop. Pretty powerful stuff. Not only does it allow you to write extensible code, but it's simply a much cleaner way of writing it. I do rather enjoy it. Finally, I have started using a new function, memory.ready. We want to return self.memCounter greater than or equal to the batch size. So you don't want to sample memory before you filled up at least a single batch of memories, because you're just going to be sampling zeros, or rather not sampling enough memories at all. So then let's make sure I didn't make any typos. Getar, so it's get attribute. There we go. All right, any other obvious errors? Nope. and then it's upset about too many blank lines, get rid of one. Now we have our function to handle initializing our actual memory. So what we want to do is we pass in our observation space, our observation shape, to define the size of our NumPy array, a max size and a batch size that we're going to need to pass through to the constructor for the generic buffer. So what we want to say is fields equals, in this case we're just going to set this up for a deep Q learning agent, states, actions, rewards, new states, and dones. And then our values are going to be a list, excuse me, a dictionary, sorry, a list, good grief, of types numpy zeros, and it'll be mem size by observation shape, dtype mp float 32, mp zeros, so now we need our actions, that'll be mem size dtype mp int 64. Now I have assumed that this is a discrete action space, so keep that in mind. If you want to do continuous actions, then your action parameters, your action values will be of a different shape. NumPy zeros for the rewards, we have mem size and p float 32 data type. Then we have the new states, that again gets memory size by observation shape, and using the correct bracket type, mp float 32. And then finally for our terminals, it's mem size equals bool, and then close our bracket. Now the way you make this extensible is, of course, you would pass in something like fields equals none, vals equals none, and then you can say fields equals fields or, and then vals equals vals or. And so if vals is provided, it will use that. If fields is provided, it will use that. Otherwise, it will use just this simple list that you provide. So I'm going to get rid of that. I want to write this as simply as possible for this tutorial, but that's how you would actually make it extensible by the end users. You just pass in parameters to this function, and then whenever you want to expand upon it, you simply change the parameters that you pass into the function call. Very, very simple. Then you have our new memory class, that's type. We're going to call it replay buffer, and that derives from the generic buffer class. And we can use a dictionary comprehension to handle our dictionary input. So we'll say field value for field and value in zip, fields and vals. Close the dictionary. There you go. Then you can say memory buffer equals memory, because remember, we have to actually define our memory buffer. So it's going to be this memory class, and we have to take into account the initializer for the base class, the generic buffer. So we have to pass in the max size, batch size, and fields, and then return that memory buffer. Okay, did I make any? Oh, good grief. I called it max size here. Let's do this. Mem size? No, that's not right. Mem size, and then come down here. I did it right down here, of course. Mem size. All right. Okay, so that should work. Let's do a right quit, and then we'll take a look at the main file. So if you're interested, what I've done is as part of my framework, I have split stuff out so that the networks are in separate files and directories, policies are separate things, and the agent is its own separate thing. So we no longer define the policy as part of the agent. The policy is a separate class that we import to instantiate in the main file and then pass it to the constructor for our agent. So our agent takes an online network, a target network, a memory, and a policy as input, and we use the default values for things like gamma and the replace. I encourage you to read over this code. It kind of gives you insight into how I'm writing the framework. I'm going to call it something like basic RL, simple RL, hobby RL, something like that, because it's just meant to be a framework for rapid prototyping of algorithms for individual researchers, not for scaling stuff out to the cloud or anything like that, just to run on your local machine, on your GPU, on whatever number of threads you have available. I invite you to check this out. It'll give you some insight into how I'm doing that. I'm not going to go over all the code right now. So let's just quit out of there and try to run it. Hopefully I didn't make any typos. I did. So it says initialize memory got an unexpected argument, keyword argument max size. So, oh, that's because I changed the name. So max size, I change it to mem size. Know what? No, fine. Good grief. Now I will. Yeah, okay, fine. There we go. Should have known that would be an issue. That's what you get for changing stuff on the fly. And lo and behold, it runs because I verified everything else in the code runs. And I'll let this run for a few minutes just to make sure that it learns, and that will give us the proof that we need that the sampling is working correctly. Okay, so it has ran for a couple minutes, and you can see we're getting pretty decent scores. I didn't do any hyperparameter tuning on this agent, and so I don't expect it to get perfect scores. It probably needs a little bit higher learning rate, maybe some tuning on the number of neurons in the hidden layers. But either way, we're getting really good scores. It is learning. That demonstrates that the memory actually works. Just to look at it again and kind of drive the point home, this is totally generic. You can pass in these fields as parameters to this initialize memory function and supply the values as well. Have you being the end user, you will know what you need, and so you can supply those things to the function and it will handle all that for you. Now you can also add in, say, a flag here, like a string input here, to denote the type of sampling you want to do. So in PPO, of course, we have this recall function that dumps all the memories out. That's for the calculation of the advantages. You want the advantage for every time step in the horizon that you're looking at, and then you want some shuffled batches for stochastic gradient descent on that particular time horizon. So you need a couple different extra ways of sampling the memory to make this compatible with PPO, but you just simply add that on here to this sample buffer function. So perhaps it's not the most. There may be other ways of doing this that are more extensible, but this is the way you handle the simplest method of extending classes. And this can be used in anything else, right? This is simply dependent on built-in Python keywords, type, and get attribute. These are obviously common to Python. You can use these for any type of classes, any problem you're working on where you have to have an extensible class where you don't necessarily know beforehand what type of stuff you're going to need. So that's very useful, something I hope is helpful for you. And yeah, that's all I have for this video. Make sure to leave a comment if you have any questions, if it wasn't clear to you. Suggestions for future videos, I read those and try to take those into account. Any other comments, leave them down below. If you found it helpful, please subscribe. If you want to support the channel, I do sell courses. Those are linked in the description below as well. All that's done, I will see you in the next video.